So despite all the mechanical properties that beryllium affords, we don't use it because of that third dimension of that triangle that made the pyramid, the environmental aspect of it, where there are a lot of great materials. Asbestos is great for insulation. Beryllium is great for optimum stiffness. Chromium is great for corrosion resistance. But you've got mesothelioma, you've got berylliosis, you've got carcinogen and hexavalent chrome. So those are all things that we need to consider when making a trade. With metal, when we're looking at metals, we have to look at not just their strength properties, but how do they behave in the environment? Sorry about that. What are their corrosion characteristics? What are their fatigue characteristics? Stress corrosion, cracking, hydrogen embrittlement, assembly costs, and weight are typically things that make metals less attractive when you compare them to composites. Things that make them more attractive are their isotropic properties, their durability, their resistance to impact. Here's a couple examples of metal failures that were due to essentially fatigue and environmental attack on the metal. When you're comparing metals versus composites, one of the big advantages of composites is their fatigue tolerance. This is just a nominal curve showing you that basically composites are not fatigue limited. You can essentially eliminate most fatigue characteristics from your airframe design by using composites, whereas metal, you're basically life limited due to the drastic drop in properties as that metal fatigues over its life. Other things we need to consider are, I've talked about the mechanical requirements, strength, stiffness, toughness, fatigue. They also materials need to be corrosion resistant. We need to understand how do they react to the environment. They need to be damage tolerant. I don't know if it's a goose or a crane that impacted this helicopter up in the radome here. But one of our design criteria is bird strike, because aircraft fly near birds. And so you have to tolerate that kind of impact to make sure your designs are accepting of a certain weight bird at a certain velocity. Survivability, environmental durability, solar radiation. Anybody know how hot a black surface in a desert might get to if an aircraft is sitting out there on a tarmac? Any guesses on how hot that might get? Too close. Okay, yeah. So it's we typically design for 220 degrees Fahrenheit for that solar radiation environment. We also have exhaust coming from the aircraft itself, that exhaust impingement, particularly with helicopters. When you're flying in several different directions, you can get exhaust impingement on those structures, and you need to understand how hot that is and how long that duration is. Sandstorms, rainstorms, among the most erosive environments that a rotor blade will see are caused by sand and rain. Environmental effects like lightning strike. You need to protect the aircraft from lightning. Has anybody ever been on an airliner that's been struck by lightning? You'll be thankful that we account for it when we're doing the design process. Basically, you need a conductive surface on the shell to keep the lightning on the surface so it doesn't penetrate and destroy the structure. Another thing we need to consider are the integration of the system. And those of you that are mechanical engineers, maybe all you engineers, probably in your early structures or maybe physics classes, learned about resonance, natural frequencies, and they probably showed you an example of the Tacoma Narrows Bridge hitting natural frequency. Well, in airframe structures, we also need to be concerned about natural frequency. This is a CH-147, and one of the things you need to be concerned with is ground resonance. So the natural frequencies of that aircraft, as it starts to react with the ground, the proximity of the ground, is something you need to account for in design, because it can literally whirl itself apart due to ground resonance if you don't properly design for those natural frequencies. Another thing we have to design for is crashworthiness. We talked about bringing people home every time, everywhere, every time. One of the big design factors for rotorcraft is it has to survive an impact, typically on the order of 35 to 42 feet per second, which is a crash condition. We have to design it so the occupants survive that kind of impact. And one of the ways we do that is with a crash test, where we literally, this was done at NASA, this was an all-composite aircraft, and part of the features of that aircraft incorporate, and Dr. Arabi and I were having this discussion as we were coming over here, when you design for crash, are you designing for the vehicle to survive? No, you're actually designing for the occupants to survive. So you're using the vehicle to absorb that energy. So the breaking off of the tail cone, the stroking of the landing gear, the crushed tub underneath the cockpit area are all designed to absorb that energy so the occupants will survive. One of the other things we need to consider is the cost of manufacturing. With metal parts, typically you have many details that are assembled with fasteners. This is very costly, very prone to error if you misdrill a hole, mislocate a hole. Plus, every one of those fastener locations is a potential corrosion site where moisture can accumulate, become entrapped. So assembly, while very mature manufacturing process, is also a very costly process. And as we look forward to the future, one of the benefits of composites is to minimize the amount of assembly by integrating several structures into one through co-cure of large composite structure and going to a fastener-free design approach. Just some reference for you. Mechanical properties, we typically do testing. I'll show you a chart coming up of how we do that philosophically. But there's also guidebooks. There's MMPDS, which is the handbook for metals, metal properties, static and fatigue. And then there's a CMH 17, which is a composite materials handbook, which will give you properties for industry accepted composites. Our approach to material characterization is something we refer to as a structural building block. The basis of that building block is material characterization at the coupon level or the element level. That's where we're running tensile tests or compression tests to characterize the basic properties of a material. We then scale that up to elements where we have frames or we have stiffeners on skins, and we're testing those typically like a 2x2 assembly in fatigue or statically to understand its behavior. That scales up then to components where we may take a full-scale blade or we may take a full-scale transmission and run it through acceptance tests to prove that the element tests and our analytical theory on how we design that part are substantiated through testing. And then ultimately we get to a full-scale aircraft where we're loading it statically and then sometimes in fatigue. And then ultimately we have ground test vehicles that we fire up, load on the ground before we actually fly that aircraft, and then leading to a flight test. Okay, now I'm going to kind of step back and look at the history. I talked about materials being, in my opinion, the center of the universe. You can't really design anything unless you're using a material, unless you're a software engineer, and then you still need something to move the electrons to apply your software. So I want to just give you a sense of history on the role of materials to the aerospace industry. Going back to 1903, the birth of the aerospace industry was the Wright Flyer. And that was actually the first use of composite materials. It's kind of ironic how we've come full circle, but the Wright Flyer consisted of natural composites, wood and canvas and some steel wire. The Irish linen had a resin coating on it to stiffen it up so it wouldn't flap too much in the wind. But one of the materials innovations that the Wright brothers used that actually made their flight possible, that may not get talked about a whole lot, is they were one of the first developers of an aluminum engine block. Most engines back in this time period were made of cast iron, and that was way too heavy. They never would have achieved their first flight if they had used a cast iron engine block. So the selection of aluminum was actually a big enabler to make flight even possible back in the 1900s. Now, that original flight went 6.82 miles an hour. So I'm going to juxtapose speed with material development and aerospace development as we step through the next series of slides. Another interesting fact about the 1900s, early 1903 to 1910, was that was the first use of synthetic plastic. Mr. Bakelin came up with this Bakelizer device, which essentially is like an autoclave, and made the first plastic parts that were useful for aircraft because they provided electrical insulation where they needed it. They were also lightweight, so they became applied to instrumentation and control knobs.